So of course, our session's being recorded. We're in section 8.3. Section 8.3 is a section on the integral and comparison tests and also estimating sums. And I have this series where n goes from 1 to infinity of 1 plus 4 to the nth power divided by 1 plus 3 to the nth power. And I want to know if that series converges. Okay, I want to know if that series converges. So what sort of is a distractor in the problem? If you look at this term in the series, 1 plus 4 to the nth power over 1 plus 3 to the nth power, that's right, Felicity. That's right, Tina. The ones are a distraction. But when n is large, are those ones going to affect how the series behaves? No, they're not. So the series, I mean, as for large n, when the terms of the series get large, the terms of the series are going to be approximately equal to 4 to the nth power divided by 3 to the nth power. So if you had the sum where n goes to 1 to infinity of 4 to the nth power divided by 3 to the nth power, what kind of series would you recognize that to be? That's right, Tina. It would be a geometric series. It would be a geometric series. So somehow this problem, I have to relate it to a geometric series. And then the question is, does the series converge or diverge? Now, the comparison test might be a little bit messy for this. Might be a little bit difficult because of the ones there. But we could use, I'm not saying it can't be done, but we could for our solution. I mean, if we don't use the comparison test, we could use what? We could use the something comparison test. Do you remember the name? Well, not integral. Not integral. I'll give you a little hint here. LIM. Good, Cologne. The limit comparison test. Good. So we're going to let a sub n be 1 plus 4 to the nth power divided by 1 plus 3 to the nth power. Okay, that's from our series here. That's the terms of our series. What would I let b sub n be? What might I let b sub n be? Well, why don't we let that be 4 to the nth power over 3 to the nth power? okay, which incidentally is 4 over 3 to the nth power. The limit comparison test says study the limit as n goes to infinity. Study the limit as n goes to infinity of the ratio of the terms from the one sequence to the terms from the other sequence. So remember, when you're computing a series, you're adding terms of a sequence. And what determines whether the series converges or diverges is how the sequence behaves as n gets large. Okay. And you're adding the terms of that sequence. So of course, then this is what I'm computing here. And of course, this is as the limit as n goes to infinity. Are there any questions so far? All right. Well, so let's see here. Now, just thinking about this. Could write this like this. A fraction divided by a fraction, so I'm going to multiply the top fraction by the reciprocal of the bottom fraction. Okay. And then I could rewrite this. I think the writing's fine, but let me know if there's anything you don't understand. Okay, so I just rewrote the product of the fractions here, as you see below. Okay, are there any questions? All right, well, let me ask you then, as n goes to infinity, What does this 1 plus 4 over n, 1 plus 4 over n divided by 4 over n go to? What does that approach? That first term there. That goes to 1. Very good, Cologne. Because the 1 isn't going to affect it as n is large. What about 3n divided by 1 plus 3n? That goes to that goes to 1 also. So you get a 1. You get a 1. Okay, so now then, and I'm thinking, I'm trying to see if I can actually move the page down, but I'm not sure. I guess that's something I've never really needed to worry about. Let's see here. But I can fit it on this. It's fine. It won't be in any way. So the ratio of the terms of the sequence approach 1 as n goes to infinity. This means then, so for, so now in the solution, I'm going to go over here. Okay, I'm going to go over here. Going over here now. So for n large, okay, for large n, our series behaves okay, it's going to behave like the series like this geometric series. Because remember, 4 over n divided by 3 over n is the same as 4/3 to the nth power. So when n is large, our series behaves like this series here, this geometric series. Does that geometric series converge or diverge? Why does it diverge? That's right, Cologne. Why does this series diverge? That's right. Very good. Because the common ratio, which diverges, because the common ratio is 4/3 that's greater than 1. Greater than 1. Geometric series, if their common ratio, or absolute value of the common ratio, is greater than 1, those those geometric series diverge. So therefore, R series diverges. It has to. And R series diverges as well. And R series by R series, of course, I mean R series, right? R series diverges as well. Because the terms of our series resemble the terms of that divergent geometric series when n is large. Sometimes you need time. Well, I'm thinking of an analogy here, but you can't tell if a series is going to converge or diverge based on just a few terms of the series, right? You have to go out and see how the series behaves when n is n is large. How does the series behave as you go out into the series? How do the terms of the series behave? Well, in our problem, our series, the terms of the series behave like that divergent geometric series, and so therefore our series has to diverge as well. Okay, so it's kind of like, I don't know, I was thinking of an analogy, kind of like maybe dating. You know, I think you need, like, you know, you can't really tell if relationship's going to work out based on a few dates, right? You have to have a lot of dates. You have to go out. You have to have like time, right? That's how I think of a series. I don't know if that's a good analogy or not, but it works for me. All right, are there any questions on that? So I wanted to do this problem just because you're going to see it in your, like, the new exercises on new section 8.3 exercises, and you know you're going to be given series that might look kind of funny, you know. Like I was thinking some of you, if you saw this series here, you know, it does, the terms of the series it is interesting. 1 plus 4 to the nth power divided by 1 plus 3 to the nth power. But just remember, it's how the series behaves as the terms get large that determines if the series converges or diverges. And the little numbers here, the ones, don't affect the terms when n is large. They don't distort the behavior. Because 4 to the nth power is much greater than 1, and 3 to the nth power is much greater than 1 also. Let me ask you this: what if when n is large? What if instead of 1, what if you had like you know, 1,000,000? Let me see here. I don't want to mess up what I have here. So instead of the ones, what if you had like 1,000,000 plus 4 to the nth power on top, and then on the bottom you had 1,000,000 plus 3 to the nth power on the bottom? Would the series converge or diverge then? Does the fact that if you have 1,000,000, instead of if we replace those ones by 1,000,000, does that affect it? That's right, Rodrigo. The series is still going to diverge because eventually 4 to the nth power for n large and 3 to the nth power for n large are going to be much larger than 1,000,000. Okay. And so all right. So Any questions on that? Okay, well, I'd like to bring up the ebook then. I'd like to bring up the ebook. Just give me one moment here. I'm going to bring it up. I want to show you a theorem from section 3. Okay, called the remainder estimate for the integral test. Okay, so let me find it here. So I wanted to do that example with you that I just did because I think the comparison test, people have an easier time with that test than the limit comparison tests. So good, here we go. So on that note here, all right, so this is in the recording. Bye-bye. Okay, so, all right. So we have situations where if the series converges, we want to find an estimate of the sum of that series. Now, of course, if you have a geometric series, you have a formula to find the sum of that infinite series. If you have a telescoping series, it's possible to get the sum of that infinite series. But other types of series that converge, where the terms are positive, decreasing, and they converge, there may not be a formula to find the sum of the infinite series. So we have to estimate the infinite series, but whenever we estimate something, there's an error. And so that's what this, or a remainder. Okay, so if you were to take the S, okay, like in this formula, well, let me see here. This always happens. I don't know why it switches on me. All right. So in this formula, the S is equal to the infinite series. It's the value of the infinite series, which we may not be able to find. Okay, but we can estimate the series, the infinite series, by adding up the first n terms of the series. When we do that, the difference between the sum S of the infinite series and the sum of the first n terms, S sub n, that's the nth partial sum. You've had a little experience doing that in your homework, finding some partials. The difference between the infinite series sum S and the nth partial sum S sub n is called your remainder, your R sub n remainder. And that remainder is, we want to get an estimate of it. Okay, and using these figures 3 and 4, okay, they get, and I'm gonna actually have my own version of that, but they have a formula for to approximate the remainder R sub n, or the error in approximating a infinite series with a partial sum with the first n terms of the series. The error in the approximation, or the remainder R sub n, is less than or equal to the improper integral from n to infinity of f of x dx, and it's greater than or equal to the improper integral where your bottom number is n plus 1, you know, it's the r sub n is greater than or equal to the improper integral going from n plus 1 to infinity of f of x dx. So this is the remainder estimate for the integral test. We're going to apply this, but let me just show you how they get this. Okay, I want to show you how they get this. Right, so let me just bring it up here. Now, I'm going to have you copy the sample down, but I don't want you to copy what I'm showing you here down. Okay, I just want to talk about it and then get to the example. Okay, but what you have here is, first of all, so what I'm trying to do is motivate you how they get the remainder estimate for the integral test. Okay, so first of all, so I just want you to relax and not take any notes on this. So S is the sum of our infinite series. Okay, just ignore that ringing. You know, everybody's calling. Everybody wants your money, right? All right. So what I've done is I've drawn this. Hold on here. Just put this out here. Okay. It's got to be a law against this kind of stuff, you know. Got to be a law, you know. So I have here a function f of x that's continuous, positive, and decreasing. And notice that the nth term of the series I'm defining as f evaluated at n. Okay, so like for instance, now I want to mention, I'll just mention this. So, you know, a sub n is equal to a sub n times 1. Okay, so for instance, a sub 6 here, a sub 6. So let's the a sub 6, let's say the value of a sub 6 is equal to this number here. I draw, so a sub 6 equals this value, which would be equal to f sub 6, right? A sub 6 would be equal to f sub 6. So when x equals 6, okay, you know, I do have an x-axis here. When x equals 6, the function and the sixth term of the sequence agree. But I can also write a sub 6 as a sub 6 times 1. So since a sub 6 is the height, I can then think of 1 as the base, and I can represent a sub 6 by the area of that rectangle. Okay, I mean a sub 6 is a number, but it can be represented as an area of that rectangle. And a sub 7 can be represented, which is the seventh term in the series, that can be represented by that rectangle there. Well, you'll notice that the rectangles are, the area of the rectangles falls below the area of the function. So if we're interested, of course, if we look at the area underneath the function going from 5 to infinity, and we compare that to the sum of the terms. And I'm just choosing to start with a sub 6. I could have started with any number, but if we have a sub 6 plus a sub 7 plus a sub 8 and so forth, that would be the terms of that series would have to be less than or equal to this integral based on the picture, because you have area here that is missing, right? So the area underneath the function is certainly more than the areas of these rectangles, and the areas of the rectangles are the terms of the series. So we can say then that the remainder sub 5, which is the difference between the sum of the series and the first 5 terms of the series. I mean, after all, the first 5, what S sub 5, right, would be equal to a sub 1 plus a sub 2 plus a sub 3 plus a sub 4 plus a sub 5. It's the fifth partial sum, so it's the first 5 terms of the series. The sum of the first 5 terms of the series. But then the remainder, r sub 5, which is the error in approximating the true sum of the series with S sub 5, the error would be simply the terms that you didn't include in the sum, which would be the 6th term plus the 7th term and so forth. And by the picture above, this r sub 5 is less than this improper integral. All right, are there any questions on that? All right. Well, now what I've done below is I've redrawn this function. I've redrawn it. Okay, exactly the same function. And what I'm doing now is I'm looking at, the a sub 6, the 6th term, and the 7th term. The areas of those rectangles are just the same as I've drawn above. Okay, but if I consider the improper integral starting, instead of at 5, starting at 6, x equals 6, then this would be, this would be my, this would be my area, right? Well, you'll notice then that the rectangles, the areas of the rectangles are going to be more. If we add up the areas of all the rectangles, which are the terms of the series, starting A6, 6th term, 7th term, and so forth, the areas of those rectangles, which is the areas of those terms, those terms, that's going to be greater than or equal to this improper integral. Okay, so the book shows that in figures 3 and 4, section 8.3, but I thought it would be helpful to have a concrete example. So what we're saying then is that the r sub 5 remainder in approximating the infinite series with the sum of the first 5 terms, that remainder, that error, is between these integrals, between those integrals. And we just showed it on the previous page. And so therefore, in general, for any function that's continuous, positive, and decreasing, the error or remainder in approximating the infinite series with the nth partial sum would be less than or equal to to the improper integral from n to infinity f of x dx, and greater than or equal to the improper integral from n plus 1 to infinity f of x dx. Okay, and of course, this is the notation that we're using here, you know, for our remainder. And I motivated that. I emphasized that earlier. The thing that we're most interested in, of course, is having a bound on our error, on our remainder, an upper bound. Okay, we'd like to know, you know, what would the error at most be? What would the error at most be? Okay, we want to know that. It's just like let's see here. Hold on. It's just like in section 5.9 when we did approximate integration with like the midpoint rule, trapezoidal rule, and so forth. The errors in those approximations, we had error bounds, upper bounds. Okay, so that we can say that the error is going to be no more than this. Okay, if we approximate an integral using a midpoint rule with a certain number of subintervals. We have, how many recall the error bounds from section 5.9 for midpoint rule, trapezoidal rule, and so forth? How many remember those? Okay, Justice remembers them. Michael does, sure. Tina and many of you. Well, this is really the goal here. The goal here. Thank you, everyone. Really, this is what we care about, is this part of this formula. But it's nice to be able to have an upper bound, you know, so we can get an idea of how far off are we, or what's the most we would be off by approximating a infinite series with a partial sum, an nth partial sum. All right, are there any questions on that before we go to an example? Okay. Okay, well, let's go ahead and look at an example here. Okay, let me give you a moment to copy this example down. Now, this you want to have in your notes, and you can always refer to the recording if you want to see, you know, what we just talked about. Okay, I'll let you copy this example down. Okay, so here we have a series, and we want to estimate this series correct to 2 decimal places. Okay, correct to 2 decimal places. So the idea here is that we could we could, I mean, like what you've done before is you've, like, the question will say, add the first 10 terms of the series, right? But remember that one problem where you had to add the first 2 terms of the series, and this is on the exam, then the first 3 terms of the series, and the first 4 terms of the series, and eventually, hopefully, you get an idea of what the sum of the series is. Remember that problem? Okay, Cologne remembers it. Okay, now how could you forget it, right? So, and there's a reason for that. It's to help you understand about series and about convergence and so forth. This series here, let me ask you, does this series converge? I mean, they're saying estimate this series correct to 2 decimal places. Does this series here, we want to know, first of all, if it converges. And I can tell you, it would kind of be silly to ask this question if it didn't converge, right? I mean, it might be a little, I mean, how can you estimate well, I want to be a little careful what I say. We can always add up terms of a series. But in this case, I can tell you this series converges, because what kind of series is this? What kind of special series is this? There's a special name for this series. You remember what it's called? Well, it's not a geometric. You could, okay, and I appreciate all. Let me clarify why it's not a geometric and why it's not a harmonic. Okay, I appreciate the responses. It's a piece series. That's right, Alan. This is a very good. So you could write this series as like this, right? You could write the series this way. But the 1 over n is not a common ratio. That's changing all the time. So it's not a geometric series. Has to have, you would have, first of all, the n in the exponent, and then you would have a fraction or number as your ratio. So it's not a geometric series. And if it were a harmonic series, then a harmonic series would be this. Harmonic series would be this. Okay, this is a harmonic series, which is a p series with p equals 1. One moment. One moment, class. Hey, Alan. Okay. Okay. So okay. Okay. Here we are. Here we are. This is a p series. What's the value of p? P series. Good, Cologne. P equals 4. And 4 is greater than 1. So the series converges. But it's not like geometric series, we'll see, think about it like this, a geometric series, if your common ratio is greater than 1, that series diverges. But for a p series, which is a totally different series than a geometric series, p series will converge if p is greater than 1. So this series is going to converge this series does have an answer. There is an answer for the value of this infinite series, but we don't have a formula to find the sum of that infinite series. So we're going to estimate the series. But we're going to be happy if our estimate is correct to 2 decimal places. So what we need to do is the question is, you might say, well, okay, how many terms of the series do I add? Am I going to add 10 terms? Am I going to add 1,000 terms? Am I going to add 1,000,000 terms? How many terms of the series do I need so that my series is correct? So that the estimate is correct to 2 decimal places. Question? Yes, Marcella. Okay. So what we're going to use to help us is we're going to use the remainder estimate for the integral test. So I go to the next page. Okay, and first of all, I want to note that the function, okay, with 1 over x to the 4th, which corresponds to the t series of 1 over n to the 4th, it's a continuous positive and decreasing. So therefore, the integral test applies. See, we can't just use this remainder estimate for the integral test on any series. It has to be where the terms of the series are positive, decreasing, positive and decreasing. So, all right. So by the remainder estimate for the integral test, the remainder is less than or equal to the improper integral from n to infinity of 1 over x to the 4th dx. Okay, so again, what I'm trying to do here is I'm trying to determine how many terms of the series do I need to add, and then once I know that, I'll add then the necessary terms. We don't want to waste time, right? So the remainder is less than or equal to the improper integral from n to infinity of 1 over x to the 4th dx. And now this is section 5.10. We got to figure out what this improper integral is going to equal. The improper integral will converge. That's not a problem. It will converge because it's a p integral, right? And of course, we write the improper integral as the limit as t approaches infinity of the definite integral from n to t of x to the negative 4th dx. So t, infinity gets replaced by t. I'm going to recall that from section 5.10, improper integrals. Tina remembers it. Rodrigo remembers it. Sure. So the antiderivative of x to the negative 4th is x to the negative 3rd over negative 3. And then I'm just going to factor out negative 1/3. I can factor that out in front of the limit. And write this as negative 1/3 times the limit as t approaches infinity. And then, of course, I'm going to put in my t and my n. I'm going to put that in in there in my antiderivative. And of course, 1 over t cubed goes to 0 as t goes to infinity. So this gives me 1 over 3n cubed. So we've established then that the remainder, r sub n, is, I want to be careful here, the remainder, well, I'm not writing that quite right. I want to say this the right way. Okay, so based on this, we can say that the remainder is less than or equal to 1 over 3n cubed. So the error in approximating this infinite series, the series where n goes from 1 to infinity of 1 over n to the 4th power, the error in estimating that series by adding the first n terms of the series, that remainder, that error, R sub n, is less than or equal to 1 over 3n cubed. So far, are there any questions? Okay. Well, now in the problem, it said we wanted to estimate the series correct to 2 decimal places. What that means then is, you see, we're going to take this upper bound here on our remainder. We're going to take that upper bound, and we're going to set it less than or equal to 5 over 10 cubed. Because we want our estimate to be correct to 2 decimal places, I have 10 to the 3rd power in the denominator, and I have a 5 in the numerator, which incidentally will be equal to 0.005. Okay, so now, like if in the problem, if they said estimate the series correct to 4 decimal places, well, then on this part here, we would take our upper bound, 1 over 3n cubed, and set it less than or equal, if we wanted the estimate correct to 4 decimal places, we would have then here, we would have 5 divided by 10 to the 5th power. Okay, and the reason you have it's so that the rounding is correct. You have to have that value. You have to have 5 divided by 10 to the power. The power is always 1 more than the number of decimal places, and that's so that you ensure that you have the precision that you want. Now we have to solve for n. So, well, are there any questions? Are there any questions so far? I mean, I'm looking here. Are there any questions so far? Okay, very good. Very good. Wait, hold on. Oh, Tina's asking about that 5 over 10 cubed. So because we want our estimate of the series to be correct to 2 decimal places, we have in the denominator 10 to the 3rd power. So 3 is just 2 plus 1. If we wanted the estimate to be correct to 4 decimal places, we would have 4 plus 1. We would have 10 to the 5th in the denominator. And the 5 in the numerator is just there to ensure that you get the precision you want. All right, Tina, does that make you feel a little more comfortable? All right, it'll always work that way. Whenever they say correct to a certain number of decimal places, so suppose they wanted like find the estimate correct to 7 decimal places. Okay, what are you going to have then? You did 7 decimal places. You'd have 1 over 3n cubed is less than or equal to 5 is for the rounding. That's correct, Michael. 5 is for the rounding. That's right. So you round in the right way. Exactly. So if you wanted your estimate correct to, what did I say, 7 decimal places, then 1 over 3n cubed would be less than or equal to 5 over 10 to what power? That's right, 10 to the 8th power. Okay, so all there is to it, really. And now what we have to do is we have to take this inequality here. So you just have to be sure that I want to be careful what I say here, but if you have like 4.567, okay, 4.567. If you rounded that to 2 decimal places, what are you going to get? So Tina, I think this will answer your question. Tina's asking about how is the 5 used for rounding? Basically, why is it there? Okay, let's look at this. Suppose you had, now we're not done with the problem yet, but we'll get there. 4.567 rounded to 2 decimal places is 4.57. But if you had 4.564, and notice 4 is less than what number? 4 is less than what number, class? 4 is less than 5. What's this gonna round to? It's gonna round to 4.56. So you see, if your estimate, sure, you're welcome, and I appreciate the question, Tina, and that's why I like students participating, and I acknowledge that. See, if the 5 and 6 are correct, if those decimals are correct, we don't want the rounding to change those decimals. That's why you need to have less than 5. That's why you have a 5 here in there. So very good. Okay. So now what we got to do is solve the inequality. So 1 over 3n cubed. Okay, if I take 1 over 3n cubed here, maybe I'll just add a little step here. 1 over 3n cubed is less than or equal to 5 over 10 cubed. So if I multiply both sides, okay, if I multiply both sides by 3n cubed, I'm going to get this inequality here. And by the way, the inequality sign didn't change, did it? Did not change. Why didn't it change? I thought sometimes inequalities, when you multiply through by a number, the inequality sign can change. Why didn't our inequality sign change? What can you tell me about 3n cubed? 3n cubed for any n is positive. N is an integer. It's a positive integer, has to be. It's the number of terms you're adding. So yeah, so good, Rodrigo, good, Cologne. So then n cubed is going to be greater than or equal to 1,015ths, 1,000 over 15, 1,000 over 15. And I'd like to move to the next page if we're good. Are we good so far? All right. All right, well, let's continue here. So n cubed, I'm rewriting it so that the variable's on the left side. N cubed is greater than or equal to 1,015ths, which means n is greater than or equal to the cube root of 1,015ths, which means n is greater than or equal to 4.0548. So how many terms do you need then? How many terms do you need? To estimate this series correct to 2 decimal places? Well, n is greater than or equal to 4.0548. Is 4 enough? No, it's not. Michael's right. You need 5. So in terms of algebra, n is, as a variable, n is greater than or equal to 4.0548. But I can't add 4.0548 terms. So to get what I need, I have to add 5 terms. And so what we do then is we add the first 5 terms of the series. So our sum is approximately equal. Our infinite series is approximately equal to the sum of the first 5 terms of the series. That's S sub 5, right? That's what this is. S sub 5. And this is what your calculator will give you. 1.08035192.29. The reason we need 5, Felicity wonders 5. Well, your n was greater than or equal to 4.0548. So that tells me, can I add? I can't do 4 terms because n equals 4 is not enough. I need at least 4.0548 terms. But how can I add 4.0548 terms? Can't add that. I got to add, I can add a integer number of terms. So if n has to be greater than or equal to 4.0548, then n has to be at least 5. Felicity, are you comfortable with that? Okay, good, good, good. You're welcome. You're welcome. So, okay. So what I do is, we get the 5th partial sum here. But what I did was, this would be like in WebAssign, this would be your answer. This would be your answer. But what I wanted to do is I wanted to add 6 terms and show you that by adding another term, it doesn't change the 2 decimal places here, the 0 and the 8 coming after the decimal. It doesn't change those. So there's no question that 1.08 is the answer. It is our estimate of this infinite series, and that's correct to 2 decimal places. And 1.08 would be what you would put in WebAssign. Okay, and that's how we use the remainder estimate for the integral test. That's how we use it. And it's really a very, it's important because, you know, even, I mean, we have computers, right, that can add things quickly. But, you know, even computers, if you keep adding terms, it's going to take time, right? Trillion terms, I don't know, gazillion terms, whatever. So it is always helpful to know, you know, if you have a certain precision that you have in mind, and, you know, if you're talking astronomy, it may be out to the 20th decimal place, who knows? You know, but if you have a certain amount of precision in mind, it's very helpful to know how many terms of the series you're going to need to add so that your estimate for the infinite series it has that precision. It's very helpful. Okay, do you see that? Is that I mean, then, you know, when you program your computer, how many have done like do loops or for loops in computing? Maybe in a computer class, like, you know, yeah. So I'm seeing a lot of people here. So, you know, you do I equals 1 to n, something like that. Okay, you program your code to add up the terms of the series. Well, where are you going to stop? Where are you going to stop? What's your stopping value of n? It depends on the precision you want. It depends on the precision that you want. How many think this is kind of cool? Okay, kind of cool, kind of good. Okay. Well, yeah. Good things take time, sometimes can be, but and of course, you know, we were you know, going in some detail covering it, but it seems that we have some students that like it, and that's very good. Very good. So let me stop the recording if there are no questions.